Hello everyone, today I am going to explain solving linear homogeneous recurrence relation with a constant coefficient. In that theorem 1, the statement says that let C1 and C2 be real numbers. Suppose R square minus C1R minus C2 is equal to 0 has two distinct roots, that is R1 and R2, then the sequence AN is the solution of the recurrence relation. Okay, so that AN is equal to C1 A n minus 1 plus C2 A n minus 2. If and only if AN is equal to alpha 1 R1 raised to n plus alpha 2 R2 raised to n for n value 0, 1, 2, 3 so on, where alpha 1 and alpha 2 are constants. So let's begin with the proof. R1 and R2 are characteristics equation of this. Okay, and alpha 1 and alpha 2 are constant. It is already mentioned in the statement. Now AN is equal to alpha 1 R1 raised to n plus alpha 2 R2 raised to n is the solution of recurrence relation. Now in the statement they have given here two distinct roots, R1 and R2. I have considered this from the statement. So R square minus C1 into R minus C2 is equal to 0. Take this on the right hand side. You will get R square is equal to C1 R plus C2. Now if I consider R1, then R1 square is equal to C1 R1 plus C2 in this equation. If I consider R2, then R2 square is equal to C1 R2 plus C2. Now this equation is given in the statement. AN is equal to C1 A n minus 1 plus C2 A n minus 2. Now this right hand side part I have written here. Okay. Now C1. Instead of A n minus 1, I am going to write alpha 1 R1 n minus 1. I am going to write here n minus 1 plus alpha 2 R2 n minus 1 plus C2. Instead of A n minus 2, I am going to write again alpha 1 R1 n minus 2 plus alpha 2 R2 raised to n minus 2. Okay. Now multiply this C1 for both this. So I have multiplied. Okay. C1. Multiply this C2 for both. So I have multiplied. In this 2, what is common? You can see here alpha 1 from here and here, and I have taken R1 n minus 2. So what is remaining here? Alpha 1 R1 is remaining. Okay. So you will get this n minus 1 plus from here C2 plus from these two what is common? Alpha 2 R2 n minus 2 is common. So here C1 R2 raised to 1 plus C2. Now this entire term from here is R1 square. So I'll write here alpha 1 R1 n minus 2 R1 square plus alpha 2 R2 n minus 2. This from here it is R2 square. You can see minus 2 plus 2 get cancelled, plus 2 minus 2 get cancelled. So what is remaining? Alpha 1 R1 raised to n, and here alpha 2 R2 raised to n. Fine. From here it is AN. This is the solution for recurrence relation. For n is equal to 0, 1, 2, 3, the initial conditions are A0 is equal to C0. A1 is equal to C1. Substituting in this equation, AN is equal to alpha 1 R1 raised to n plus alpha 2 R2 raised to n. From here just now we have proved. These are the initial conditions. So where there is a n, substitute 0. Okay. So here there is a n 0. So here there is a n 0. As anything raised to 0 is 1. So you are remained only with the alpha 1 plus anything raised to 0 is 1, so you remain with the alpha 2. So this is your C0. Now if you substitute n value as a 1 here, okay, you get A1 is equal to C1 alpha 1 R1 raised to 1 plus alpha 2 R2 raised to 1. Now here keep this alpha 2 as it is, take this alpha 1 on the left hand side, so it will become C0 minus alpha 1. So in this equation substitute alpha 2 value, write this C1 alpha 1 R1 plus alpha 2 value is C0 minus alpha 1 into alpha 2. Okay, now into R2, multiply this C1 alpha 1 R1 plus C0 R2 minus alpha 1 R2. In this 2, what is common? Alpha 1 is common. C1 alpha 1 R1 minus R2, okay, plus C0 R2. If you take common in these 2, you will get alpha 1 and R1 minus R2 plus C0 R2. Now take this C0 R2 on the left hand side. So you will get C1 minus C0 R2 and this goes to the denominator part, that is R1 minus R2. So what do you get? Alpha 1. Now alpha 2 is equal to C0 minus alpha 1 from here. Okay. Now C0 minus, what is alpha 1? C1 minus C0 R2 divided by R1 minus R2. Fine. Now cross multiply this. If you cross multiply C0 R1 minus C0 R2. Now take this minus inside. C1 minus into minus is plus C0 R2 whole divided by R1 minus R2. You can see here minus plus get cancelled. So what is the final answer? C0 R1 minus C1 divided by R1 minus R2. So this is your alpha 2 value. Now let us consider one example. What is the solution of recurrence relation an is equal to an minus 1 plus 2 an minus 2 with the initial condition a0 is equal to 2, a1 is equal to 7. Okay. Now these are on the right hand side, bring it on the left hand side. Okay, an minus an minus 1 plus 2 an minus 2 is equal to 0. Here the degree is 2. So I am going to write r square minus r plus, no, this will become minus because it's going to the left hand side. Fine, is equal to 0. Now you can solve this by calculator or by factorize. Okay, so if you solve this by factorization method, minus 2 plus 1, so the roots will be r1 will be plus 2 and r2 will be minus 1. Fine. Now once you get this, substitute in this formula. An is equal to alpha 1. What is r1? It is 2 raised to n. Alpha 2, r2 value is minus 1 raised to n. Okay. Now what are the initial conditions? a0 is equal to 2. Now where there is a n, substitute 0. So this will become alpha 1 plus alpha 2 because anything raised to 0 is 1. Now next initial condition is a1 is equal to, substitute n value as a 1. So alpha 1 r1 plus alpha 2 r2. Okay. Now what is r1 value? R1 value is 2 and R2 value is minus 1. These two equations solve from calculator, you get alpha 1 value as a 3 and alpha 2 value as a minus 1.